The universe is 13.8 billion years old, but the edge of what we can see is not 13.8 billion light years away. It is about 46.5 billion light years away. And that is only the first disturbing part.
Some galaxies we can still see in our telescopes today are already beyond our reach forever. Their ancient light can still arrive here, but if we sent a signal to them now, that signal would never reach them. Space between us and them is expanding too fast.
So the edge of the universe is not a wall. It is not a place where stars stop. It is not a cosmic border with darkness on the other side. It is a horizon, a limit created by the speed of light, the expansion of space, and the age of everything. But then, the question becomes much darker. If this is only the edge of what we can observe, what is hiding beyond it? More galaxies? Infinite space? Another region of the same universe? A curved reality that wraps back on itself? Or could our visible cosmos be only one bubble inside something much larger? According to NASA, the observable universe is only the part of reality from which light has had time to reach us. According to the Planck mission, the oldest light we can directly study is the cosmic microwave background, a faint afterglow from when the universe was only about 380,000 years old. But that ancient light is not perfectly smooth. It contains tiny scars from the early universe. Most of those scars fit our best cosmological model beautifully. But a few of them are strange enough that scientists still debate whether they are statistical accidents, hidden foreground effects, or hints that our model of the universe is incomplete. So before we ask what lies beyond the edge, we have to understand something even stranger. The edge may not be the end of the universe. It may be the end of our information. Take a deep breath and look around you. Everything you see, the room, the planet, the sun, the Milky Way, the distant galaxies, every shining structure ever photographed by a telescope belongs to a single bubble of visibility. This bubble is called the observable universe. It is enormous, beyond normal imagination. Its radius is about 46.5 billion light years, meaning the full diameter of what we can observe is about 93 billion light years across. But this does not mean the universe itself is 93 billion light years wide. It means that this is the size of the part that can be connected to us by light. And that distinction is everything. Because when we look into space, we are also looking into the past. We see the moon slightly in the past. We see the sun as it was about 8 minutes ago. We see nearby stars as they were years ago. We see distant galaxies as they were billions of years ago. The farther we look, the older the universe becomes. At some point, we reach a distance where galaxies begin to disappear, not because space ends, but because we are looking back to a time before galaxies existed. And then we reach the oldest light. According to ESA's Planck mission, the cosmic microwave background is the furthest back in time we can explore using light. It was released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into atoms. Before that moment, space was not transparent. The young universe was filled with charged particles. Photons could not travel freely. Light was constantly scattered, absorbed, and re-emitted. The cosmos was more like a glowing fog than the empty darkness we imagine today. Then, the fog lifted. The first freely traveling light began moving through the universe. Over billions of years, the expansion of space stretched that light into microwaves. Today,
It reaches us from every direction as a faint radiation, almost perfectly uniform, but carrying tiny temperature differences that later grew into galaxies, clusters, and the cosmic web.
This is often called the baby picture of the universe. But even this baby picture is not a photograph of the absolute beginning. It is only the earliest light we can see. Behind it, there were earlier moments: inflation, quantum fluctuations, perhaps physics that our current theories cannot describe. So the first answer to the question, what is beyond the edge, is surprisingly simple. Beyond the edge of the observable universe, there is probably more universe.
More space, more matter, more galaxies, more cosmic voids, more dark matter, more ancient radiation, more structure that we cannot see because its light has not reached us, and in many cases, never will. But that simple answer opens a much larger problem, because the edge of the observable universe is not one edge. It is several different horizons layered over one another.
The first is the particle horizon. This is the limit of what we can see today. It marks the farthest distance from which light has had time to reach us since the universe became transparent. The second is the event horizon. This is more disturbing. It does not describe what we can see now. It describes what we can ever receive. Because cosmic expansion is accelerating, there are regions of space whose light, if emitted today, will never reach us. No matter how long we wait, their future signals will never arrive. The third is the Hubble sphere. This is the distance at which galaxies recede from us at the speed of light because of the expansion of space. But this is not a hard wall. Light from beyond the Hubble sphere can sometimes still reach us, depending on how expansion changes. This is one of the places where popular explanations often become misleading. The Hubble sphere is important, but it is not the final border of reality. So the universe does not give us one clean boundary. It gives us horizons. And horizons are dangerous things, because they make a limited world look complete.
Imagine living your entire life on a small island in the middle of the ocean. The beach is the edge of your land. The horizon is the edge of your sight. From the shore, the ocean looks like a closed circle around you. If you had never sailed beyond it, you might think that circle was the edge of reality itself. But it would not be the edge of the ocean. It would only be the edge of what light allows you to see.
Our position in the cosmos may be similar. We are not at the center of the universe. We are only at the center of our observable universe. If an intelligent civilization lived in a galaxy near the edge of our observable universe, they would not see themselves near any edge at all. They would see their own observable universe centered on them. Some of what we see would be invisible to them, and some of what they see would be forever invisible to us. Every observer is trapped inside a different sphere of light. So when we say the edge of the universe, we are already using the wrong language. There may be no edge out there. There may only be horizons, and each horizon depends on where you are, when you are, and what light has had time to reach you. This means the real universe could be much larger than our observable universe. It could be finite, but so enormous that its curvature is impossible for us to detect. It could be curved in a way we cannot visualize. It could be infinite. Or it could be something stranger than all of those possibilities. To understand why, we need to ask a deeper question.
What is the shape of the universe? On everyday scales, space appears flat. If you draw two parallel lines on a flat surface, they remain parallel. But on a curved surface, parallel lines can behave differently. On the surface of Earth, two two lines that start out parallel can eventually meet. On a saddle-shaped surface, they can diverge away from each other. Cosmologists use this same idea for the universe itself. If the universe has positive curvature, it may be finite but unbounded, like the surface of a sphere in a higher dimensional sense. You could travel forever without hitting an edge, and perhaps eventually return to where you started. If the universe has negative curvature, it may be open, saddle-like, and possibly infinite. If the universe is flat, it may be infinite, though flatness alone does not absolutely prove infinity. According to the Planck 2018 results, when Planck data are combined with baryon acoustic oscillation measurements, the curvature of the universe is consistent with zero. In simple terms, the observable universe appears extremely close to flat. This is one of the strongest clues we have. But it does not settle the question.
The ocean looks flat from a boat. A desert looks flat from the ground. Earth itself looked flat to people who could not see enough of it. In the same way, our observable universe may be too small a patch to reveal the curvature of the whole. The entire universe could still be curved on a scale much larger than our cosmic horizon. And if that is true, then the universe may have no edge for the same reason Earth's surface has no edge. It may be finite, but unbounded. You would not reach a wall. You would not reach a final cliff. You would simply keep moving through space, and the geometry of that space would decide what straight ahead actually means. There is an even stranger version of this idea: cosmic topology. The universe might be connected in a way that makes space wrap around itself. If that were true, traveling far enough in one direction might eventually bring you back to your starting point, like walking around the surface of Earth, but in 3 dimensions instead of 2. Scientists have searched for repeating patterns in the cosmic microwave background, because a wrapped universe might show us the same ancient region of space more than once. So far, no convincing repeating pattern has been found. But the idea remains powerful because it gives us a universe with no wall, no outside, and no need for infinity. There would be no beyond the universe because space would close back on itself. But what if the universe does not close? What if it just keeps going? Then we enter the territory of infinity. And infinity is not just very large. Infinity changes everything. If the universe is truly infinite, then every physically possible arrangement of matter may occur somewhere. Not because the universe is magical, but because in an infinite space, rare events do not merely become possible. Under the right assumptions, they become inevitable. Somewhere unimaginably far away, there could be a galaxy almost identical to the Milky Way, a star almost identical to the Sun, a planet almost identical to Earth, a person almost identical to you, hearing almost the same words, with one tiny difference. According to physicist Max Tegmark, if space is infinite and matter is distributed in all physically allowed ways, then distant copies of our observable universe may exist. Not near us, not reachable, not testable with current science, but as a logical consequence of infinity under certain assumptions. This is where cosmology begins to feel uncomfortable. A large universe is humbling. An infinite universe is almost unbearable. Because if space is infinite, then the observable universe is not just small, it is 0% of the whole. Everything we have ever known, everything we have measured, every galaxy we have photographed, every equation we have built from visible evidence would describe only an infinitely tiny fraction of reality. And that raises a brutal question. Can we really understand the universe if almost all of it is forever outside our evidence? The standard answer is that the observable universe should be representative. On large enough scales, the universe appears homogeneous and isotropic. That means it looks broadly the same everywhere and in every direction. This is called the cosmological principle, and for the most part, it works extremely well. The cosmic microwave background is almost uniform. The large-scale distribution of galaxies forms a cosmic web, but when averaged over huge distances, the universe appears statistically similar in all directions. This is why modern cosmology can build powerful models from the part we can see. But almost is where the mystery lives. Because the cosmic microwave background is not perfectly ordinary. Most of it fits the standard model extremely well. That is important. The universe is not chaos. The lambda CDM model remains the most successful description of the large-scale cosmos. But on the largest scales, there are a few features that refuse to feel completely comfortable. One of them is known as the CMB cold spot, an unusually cold region in the microwave background. It may be a statistical accident. It may be connected to a huge cosmic void between us and that part of the ancient light. Or, in more speculative interpretations, it could be a clue that something unusual happened in the early universe. Another mystery is the so-called axis of evil, a controversial alignment in the largest patterns of the CMB. The name sounds dramatic, but the science is cautious. Some researchers think it may come from data processing, foreground contamination, or simple statistical chance. Others have asked whether it hints at something deeper, a preferred direction in a universe that should not have one. And then there are giant structures. Astronomers have reported enormous arrangements of galaxies and quasars, including the giant arc and the Big Ring. If these structures are confirmed as real physical features and not artifacts of selection or statistics, they may sit uncomfortably close to the limits of the cosmological principle. None of these anomalies proves that there is another universe beyond ours. None of them proves that the standard model is wrong. But they create a useful tension. Our best model says the universe should be smooth, flat, and statistically ordinary on the largest scales. The data mostly agrees, but not perfectly. And in cosmology, the most interesting questions often hide inside that word, almost. This is why the edge of the universe is not just a question about distance. It is a question about whether our visible patch is normal. If the observable universe is representative, then beyond the edge there is probably more of the same. Galaxies, clusters, voids, dark matter, dark energy, and space continuing outward. But if our patch is not representative, then beyond the edge could lie regions with different conditions, different structure, perhaps even different effective laws. That brings us to one of the strangest serious ideas in cosmology: eternal inflation. According to NASA, cosmic inflation was a period in the extremely early universe when space expanded faster than light for a tiny fraction of a second. This does not mean matter broke the speed limit. It means the fabric of space itself expanded. Inflation helps explain why the universe appears so flat, so smooth, and so similar in all directions. Tiny quantum fluctuations were stretched to cosmic size. Later, those fluctuations became the seeds of galaxies and clusters. But in some versions of inflation, inflation does not end everywhere at once. It ends in some regions while continuing in others. Each region where inflation ends can become a bubble universe. Our universe in that picture would be one bubble inside a much larger inflating reality. Some bubbles might be empty. Some might contain galaxies. Some might have different physical constants. Some might never form atoms. Some might collapse quickly, some might expand forever. And if another bubble once collided with ours, it might have left a faint scar in the cosmic microwave background. Scientists have searched for such signatures. No confirmed evidence has been found. But the idea remains one of the most haunting possibilities in modern cosmology, because it means the Big Bang may not have been the beginning of everything. It may have been the beginning of our region.
In this view, asking what lies beyond the edge of the universe becomes almost impossible, because the universe might not mean what we think it means. Our observable universe would be a bubble inside a larger multiverse. Beyond our horizon may be more of our bubble. Beyond that, perhaps other bubbles. Beyond them, an inflating background that never fully ends. But this is not confirmed science. It is a serious theoretical possibility, not an established fact. And it has a deep problem. If other bubble universes are forever beyond our reach, can we ever test them? If a theory predicts regions we cannot observe even in principle, is it physics or philosophy? This question divides scientists.
Some argue that if a theory explains our observable universe and naturally predicts unobservable regions, then those regions should be taken seriously. Others argue that without testable evidence, the multiverse risks leaving science behind. The edge of the universe is where this conflict becomes unavoidable. There is another way the universe might avoid an edge. Maybe the Big Bang itself was not an absolute beginning. Maybe it was a transition.
In the Big Bounce idea, the universe existed before the Big Bang in a contracting phase. It shrank, became extremely dense, but instead of collapsing into an infinite singularity, quantum effects caused it to rebound. The collapse became expansion. The end became the beginning. In some models of loop quantum cosmology, space itself is not continuous at the smallest scales. It has a quantum structure. Under extreme conditions, that structure may prevent the universe from reaching infinite density. Instead of a singularity, there is a bounce. If this is true, then what we call the Big Bang was not creation from nothing. It was a bridge from one cosmic era to another. There are also cyclic models, where the universe expands, cools, empties, and eventually gives rise to another universe on a new scale. Roger Penrose's conformal cyclic cosmology suggests that the infinitely expanded future of one universe could become mathematically equivalent to the Big Bang of the next. In that model, our universe may be one aeon in an endless sequence. The end of one cosmos becomes the beginning of another. Some researchers have even claimed possible hints of previous cosmic cycles in the CMB, sometimes called Hawking points. These claims are controversial, and most cosmologists do not treat them as established evidence. But the idea is fascinating because it turns the microwave sky into something like an archaeological record. Not just of our early universe, but perhaps of something before it. Then there is the Hartle-Hawking no-boundary proposal. According to Stephen Hawking and James Hartle, the early universe may not have begun at a sharp, singular edge. Instead, near the beginning, time may behave more like a spatial dimension. In that picture, asking what happened before the Big Bang is like asking what is north of the North Pole. The question seems meaningful, but the geometry makes it dissolve. There is no before because time itself does not extend past that boundary in the ordinary way. This idea does not say the universe came from a normal point in empty space. It says the beginning may not be an edge at all. It may be a smooth, boundaryless condition where our usual concepts of time fail. And then there is one of the darkest possibilities: black hole cosmology.
Black holes are places where gravity becomes so strong that beyond the event horizon, nothing can escape. At the center, according to classical general relativity, there is a singularity, a place where density and curvature appear to become infinite.
But singularities are usually a sign that our theory has broken down. Some physicists have speculated that what looks like a black hole from the outside could look like an expanding universe from the inside. In this view, our universe might have formed inside a black hole in a larger parent universe. Our Big Bang would correspond to the birth of that black hole. Our cosmic expansion would be the interior evolution of something that, from the outside, appears sealed behind an event horizon. If this were true, every black hole in our universe might contain the seed of another universe, a cosmos inside a cosmos, a chain of realities hidden behind horizons.
This is speculative. It is not the standard model. We have no direct evidence that our universe is inside a black hole. But the idea survives because it touches a real wound in physics. Both the Big Bang and black holes force general relativity and quantum mechanics into the same extreme territory. And we do not yet know how to fully combine them. That is why the edge of the universe is not only outward. There is also an edge backward in time. We can see the cosmic microwave background. We can infer what happened earlier. We can model inflation. We can calculate nucleosynthesis. We can trace the expansion of space back into a hotter, denser state. But when we approach the earliest moments, our theories begin to strain. General relativity explains gravity, space-time, and the large-scale universe. Quantum mechanics explains particles and fields at tiny scales. But the early universe was both extremely small and gravitationally extreme. To describe that properly, we need quantum gravity. And we do not yet have a complete, experimentally confirmed theory of quantum gravity. So there are two cosmic edges. One is far away, beyond the distance light can show us. The other is behind us, before the oldest light, before ordinary physics becomes clear. One edge is hidden by space. The other is hidden by time. But maybe there are ways to learn more. Light is not the only messenger in the universe. Neutrinos are tiny particles that interact extremely weakly with matter. They can pass through planets, stars, and galaxies almost as if nothing were there. They may carry information from violent cosmic events and from conditions that ordinary light cannot escape. Gravitational waves are ripples in space-time created by accelerating massive objects, such as merging black holes and neutron stars. According to LIGO, the first direct detection of gravitational waves in 2015 came from two black holes merging about 1.3 billion light-years away. This opened an entirely new kind of astronomy. We no longer only see the universe, we can, in a sense, hear it. But even neutrinos and gravitational waves cannot break the deepest cosmic limits. They still obey causality. If a region is beyond our cosmic event horizon, no signal emitted from there now can ever reach us, whether it is light, neutrinos, or gravitational waves. These tools can help us see through dust, through stellar interiors, and into extreme events. They cannot let us escape the causal structure of space-time. That is the hard truth. The universe may be infinite, but our access to it is finite. And in the far future, that access will shrink. Because expansion is accelerating, distant galaxies are gradually becoming more unreachable. Today, we can observe billions of galaxies, but trillions of years from now, future astronomers, if any exist,
may see a much emptier sky. Galaxies beyond the local gravitationally bound group will fade away, their light stretched into wavelengths too long and too weak to detect. The cosmic microwave background will be redshifted into near invisibility. The evidence of the Big Bang itself may disappear from practical observation. Future civilizations may look into the sky and see only their own island of stars. They may not know the universe is expanding. They may not know other galaxy clusters ever existed. They may believe their local cosmic bubble is all there is.
In that sense, we live at a rare moment. The universe is old enough for stars, planets, chemistry, and observers, but it is still young enough that the ancient evidence has not vanished. We can still see the CMB. We can still measure distant galaxies. We can still detect expansion. We can still infer that reality is larger than our horizon. But the universe will not preserve that evidence forever. According to the standard Lambda CDM model, dark energy currently dominates the large-scale expansion of the universe. If dark energy remains constant, expansion will continue accelerating. Galaxies outside bound groups will recede farther and farther away. Star formation will slow as gas is used up. Existing stars will burn out. White dwarfs, neutron stars, and black holes will remain. Over unimaginable timescales, even black holes may evaporate through Hawking radiation, if our understanding of quantum effects near horizons is correct. The likely result is the Big Freeze, or heat death. Not a final explosion, not a dramatic fire, just the slow disappearance of usable energy. The universe becomes colder, darker, thinner, and less able to produce structure, life, or memory. There are other possible endings. If dark energy changes over time, expansion could eventually slow or reverse, leading to a big crunch. If dark energy grows stronger, it could produce a big rip, tearing apart galaxies, stars, planets, and eventually atoms. If the vacuum of our universe is metastable, a transition to a lower energy state could spread at the speed of light and rewrite the laws of physics before anything could see it coming. These are real theoretical possibilities, but none is confirmed. For now, the best supported picture is continued expansion and eventual heat death. And this brings us back to the original question: what is beyond the edge? If by edge we mean the edge of the observable universe, then beyond it is almost certainly more universe, more galaxies, more voids, more dark matter, more cosmic web, more regions from which light has not reached us. If by edge we mean the cosmic event horizon, then beyond it are regions that can never affect us from now on. They may exist. They may contain galaxies, stars, planets, perhaps even life, but they are outside our future causal contact. If by edge we mean the edge of space itself, then we do not know whether such an edge exists. The universe may be infinite. It may be finite but curved back on itself. It may have a topology that allows space to wrap around without a boundary. Current observations show no physical edge and no measurable curvature, but they cannot prove infinity. If by edge we mean the beginning of time, then again, we do not know. The Big Bang marks the earliest hot, dense phase we can describe with confidence, not necessarily the absolute beginning of reality. Before that may be inflation, a quantum bounce, a no-boundary state, a parent universe, or something our current physics cannot yet express. If by edge we mean the edge of our theories, then we have already reached it. This may sound disappointing, but it is the most honest answer science can give. The universe is not limited by what we can imagine. It is limited by what can be measured, tested, and connected to evidence. Beyond the observable universe may be endless space, other cosmic regions, other bubbles, or a geometry with no edge at all. But until information reaches us, the beyond remains beyond. And yet, the fact that we can understand even this much is extraordinary. We are small creatures on a small planet orbiting an ordinary star in one galaxy among billions. We cannot travel to the cosmic horizon. We cannot step outside the universe and look back at its shape. We cannot see the beginning directly. We cannot receive signals from regions forever beyond our event horizon. But from a faint microwave glow, from the redshift of galaxies, from the geometry of ancient sound waves frozen into cosmic structure, from gravitational waves passing through Earth by less than the width of a proton, we have learned something profound. Our visible universe is not the whole thing. It is a bubble of knowledge inside a much greater unknown. The edge of the universe is not a wall, it is a mirror. It shows us the limits of light, the limits of time, the limits of measurement, and the limits of human intuition. And beyond it, there may not be an edge at all. There may only be more distance, more time, more structure, more silence, and perhaps more versions of the same question being asked by minds we will never meet. What lies beyond the edge of the universe? The best answer is this. Beyond the edge of what we can see lies the difference between the universe as it appears to us and the universe as it truly is. And that difference may be infinite.